Okay, the primary component of the aircraft is the structure. We have fuselage, we have the wing, we have the tail, empennage, landing gear. So those are the primary component of the aircraft. Because without the structure, we don't have the aircraft. Okay, in structure, what we have here is load. Okay, loads. Okay, loads, flight loads. So we're talking about loads. So in structure, the first thing that we talk when you talk about structure are loads. And then these are all loads. Okay, load. Then fatigue. The structure failure due to repeated load. And then lightning protection. So lightning protection basically should be under F because it's electric. However, it's in structure because lightning protection, you have to protect the structure from lightning. If the structure hit by lightning, the structure strength will be reduced. So that's why it's still under structure. Okay. In general, people ask question, what is in the subpart C? Structure is load. They're talking about loads. So where you find loads, where can you find a requirement about loads? You refer to subpart C. So here, general loads, load factor safety, strength deformation, proof of structure. Loads, you have to set the loads. How do you get the loads? Either like I said again, we set it as what we wish. For example, A320 is 120 ton. It was set as such. And then factor safety. All the structure must meet the minimum factor safety in designing for that load. So the authority require 1.5. So mean that 50%. So the structure must have a factor of 50% above the applied load. If you need to apply load 100, say 100 Newton load, your structure must be designed to 150 Newton. Because the factor of safety is 150 over 100 is 1.5. You must have that 1.5 because that is required under the design regulation. So what is 50%? 50% is to cover your error, cover your material variability, cover your environment. So that's 50%. However, the new approach of design is race-based. It's no longer set 1.5, but it's just set. You must determine, you must justify what is the design factor safety based on your design assessment. But not yet on part 25, it's already in part 23. Part 23, they remove already the factor safety 1.5 in the design requirement. So we ourselves must show what will be the factor safety. Strength deformation, you have to do analysis. You have to do the test. You must prove the structure having the strength, it will not fail, and it will not permanently deform. Aircraft structure is not allowed to be permanently deformed. If the aircraft structure is permanently deformed, means the aircraft structure had failed. So during the design under 305, you must design the aircraft to prove to have the strength, and then any deformation is not allowed. So in your design, you don't allow any deformation. 307, proof structure. So you prove structure by test. You must make sure your analysis here in 305 be supported by some kind of test. So that's why when we build aircraft, we build 3 or 4 standard aircraft. First aircraft we destroy due to the static test. The whole aircraft destroyed. That is production standard aircraft. It's not just a mock-up. And then the second aircraft will be used for fatigue test. Also will be destroyed after 5 or 6 years. Because the test may run to 5 or 6 years. And the third one will be the flight test. So minimum aircraft to be built for the certification 3 aircraft minimum. I think for Airbus they build 6 production standard aircraft. Okay, so this is load, factor safety, strength, deformation, and flow structure. The flight load, first we consider flight load. The flight load is flight maneuver and gas load. So you maneuver the aircraft you take off, you landing, you climb. So you must record all the load, because that will be the flight maneuver and gas load. You can see a symmetric maneuvering condition. So flight maneuver envelope. So you must provide the envelope, because you cannot maneuver to as many G as you want. You must have to have minimum G. So during the flight maneuver load, the designer should provide the cap. What will be the maximum, what will be the minimum G, what will be the maximum speed. So you only operate within that range. So 25333 will determine that range under the by test. Design speed, what will be the speed? Limit maneuvering load factor, again, what is the G? This is a N and G diagram. Gas, so what will be the gas and turbulent? So there is a minimum gas and turbulent. Otherwise, if you are trying to design to the very high gas and turbulent, your aircraft will come very heavy. But if you minimize the gas and turbulence, you may lose the aircraft when the aircraft encounter turbulence. So you may have the case like the Asia over Indonesia. So that could be gas and turbulence. Design fuel and oil load. So fuel is a mass. All has a mass. So the mass of fuel, the mass of oil must be considered as part of the load. So there are two loads here. The load by the air load, also the load by the mass of item itself. And the load that you receive when the aircraft hit the ground. So those are three loads you must consider in this design. High lift devices, you have spoiler, you have flaps, you have slats. Those are high lift devices. High lift devices, when you extend it, you operate it, it will cause increase in lift, so that increase in load. So you must consider that. Rolling condition, when you roll and yaw, you have also pull the load. Increase this load. The rolling and yaw, during the rolling and yaw operation, your load will be higher than the standard maneuvering load. So these are the load you need to consider in the design. Okay. So I don't think you have much on this, because you're not design new, but you only design modification. Okay. I don't want to go too deep on this one. Okay, now supplementary condition. Engine auxiliary power unit torque. As you start the engine, you produce torque. You need to consider the torque. Your engine mount, your wing structure must be designed to absorb that torque when you start the engine. Engine failure load. When engine fail, engine stop moving, or the disc ruptured and punctured the whole nacelle. So those are the things you need to consider. Engine fail. When engine fail, it create load. Sudden stop create load. Engine not functioning create drag. So you must consider it in 362. So side load engine and auxiliary power unit. Side load engine. So load on the engine on the one side. Maybe one stop, one is running. And then the load itself, when you put APU similar to engine, it has torque. It also sitting on part of the aircraft structure, attached to the structure, and this item having a mass basically, and also this item is operating and functioning. It also give load. Pressurized compartment, you pressurize the aircraft just like Coke can. It is pressurized, so you have to make sure it be able to absorb the pressurized load. So you need to design, you need to analyze the load when the aircraft structure is pressurized. You also need to do the test. You need to do fatigue test when the aircraft is pressurized, unpressurized. Asymmetric load due to engine failure, one engine off, one engine on. You need to consider that because there's a load. Gyroscopic, as the engine turning to the other side, the fuselage maybe try to turn to the other side. And speed control devices. Speed control devices, you have speed brake, you have all these flaps to brake the aircraft, then those load has to translate it to the system structure. So basically, this is they call it supplementary load. It's not primary load because it's not the load that the exhaust been transmitted through the lift of the aircraft. Okay. And control surfaces load, as you operate the control surfaces giving the load translated to your control system, to the push rod, to the bracket, to the cable, and you have to consider that. You have to calculate that. The modern aircraft, the load is go from the flaps to the push rod to the actuator, and the actuator is attached to the aircraft structure. There's no more cable, no more pulley. So now they call it, that's why they call it system interaction load. That we see in the CS. CS is considered that. FA is considered as well, but it's not clearly stated like the CS. Okay. Interaction of system and structure. So those are the load that I just explained to you. Okay. Because actuator having push rod push the control surfaces, but the actuator is attached to the aircraft structure, so they call it system interaction. Because the push rod, the actuator push rod is a system, flight control system. However, in the past there is a cable, there's a large push rod from somewhere, but now by wire is only from that actuator to the control surfaces. So they call it system interaction load. Okay, so and then ground load. So we have ground load. When you on the ground, you're landing gear arrangement, level landing, tail down landing, one gear landing, side load condition, rebound landing, ground handling, when you tow the aircraft, taxi, takeoff, landing, brake, turning, tail wheel yawing, nose wheel yawing, pivoting, reversing, towing bar, you tow the aircraft, ground load, and jacking. Now tow bar, if you have this tow barless, you don't tow the aircraft, you don't hook the aircraft direct to the stride. But however, you just grab the wheel, bring up, and then push. There's still a load there because you load the whole nose gear. You're pulling it. So still there is a load that you have to design. You have to certify this load. Okay. So that is ground load. Then water load. When you land the aircraft, general design weight center. Okay. The amphibian aircraft, the hull design just like a boat. So the lower half of the fuselage for the amphibian is boat design. You go to the amphibian that we have, CL415, the amphibian that we use by the bomber, you can see clearly half of the fuselage down is just boats. Okay? That's why they call it hull. In fact, the whole fuselage, so people call it hull. Okay. So this is a detail of the water load for the amphibian. Emergency landing. You have emergency landing dynamic condition. What are the G that you need to design the aircraft in the case of the emergency landing? So you do emergency landing, that's why you survive, because it has been considered, the G loading. Here is very important for you to do interior because you need to consider everything that you design in the cabin to survive this emergency landing. 25562. Structure ditching, if the aircraft land in the water, that's why the aircraft designed to land in the water, and you can see many aircraft landed in the water, and you can see many passengers survive because it has designed to land in the water. So that's why we have this 563 structure ditching provision. Okay, and the fatigue evaluation 25571, damage tolerant fatigue. Okay, the aircraft design, there's three design concept: safe life, fail safe, and damage tolerant. So the current aircraft mostly designed to damage tolerant. Damage tolerant means there's already damage in the structure, and we grow the damage using the fracture mechanics theory, and we determine this what is the crack growth, the crack growth rate, the crack critical length. that is damage tolerant. So that is this information we use to do the inspection. For safe life is just something like landing gear. You are not able to do anything on it. If the landing gear is damaged, it's damaged. It cannot be redundant, and it cannot having the concept of the landing gear has damage, and we grow the damage. It is safe, fail safe, safe life. Safe life means the structure having the life. Whether you reach, as you reach the life, whether good or bad, you have to remove the structure. You must retire the structure. So that is the concept of safe life. The fail-safe concept is you have redundant structure. You have bracket. You need to be safe, fail-safe. You design two bracket. Two bracket to carry the load. If one bracket fail, one bracket is still able to carry the load. Those are the concept of fail-safe. Okay, in your design. So lightning flotation, you have to protect the structure because lightning will cause heat, it cause damage the structure. So you need to have some protection. That's why most of the structure you also need the energy need to be dissipated. The current has to flow, and that's why most of the structure in design, when you do structure repair, when you do any installation on aircraft, you have to do the continuity check. I think it's around 0.05 micro ohm or something. You must have that continuity. This is a problem with the composite aircraft because composite aircraft is not conductive, and it has a problem on the connectivity. So that's why some composite aircraft they have a rod in the middle of the aircraft where they grounded everything to the rod, or they have some lead wire or something to ground it somewhere.